Okay, I think we're going to get started. So welcome to the one of this year's Stanford S. and Beverly P. Penner Distinguished Penner Lectures. This lecture series was established as a gift and endowment from Sol Penner, who was the founding chair of the Ames Department. Over the years has become the MA Department. So my name is Stefan Schmid. I'm the current chair of the department. It's a pleasure to welcome you to this lecture. We have our second lecture of the year. Unfortunately, one lecture was planned, had to be cancelled because of adverse circumstances, but we're hoping to reschedule those papas for the fall. So it's my pleasure to welcome you to this lecture today in May. Our speaker today is Peter Schmid. I'm going to lead the detailed introduction to our own Professor Schmid, spelled differently. And so I'm going to hand over the non-microphone.
Thanks. Yeah, Schmid happens, as they say. And so Stefan already complained about the length of my introduction, but then the only way to mitigate this is to invite less distinguished speakers. So today we're honored to welcome Peter Schmid. Peter Schmid is a professor of mechanical engineering and affiliate professor of mathematics at House. He held previous positions at Imperial College London, École Polytechnique, CNRS, University of Washington. People is known to everybody in this, I would say, in the field of fluid mechanics, and a very well-known figure in applied mathematics. He received his degree in aerospace engineering from the University of Munich and his PhD in mathematics from MIT. And Peter is a fellow of the American Physical Society. He's a Gordon and Betty Moore scholar and an overseas fellow of Churchill College at Cambridge University. Peter is known for his pioneering work on non-modal stability theory. He's also the lead author of this wonderful textbook on the topic, which, as a poor graduate student, I could only afford in the illegal import softcover version. But Peter is probably best known now for the invention of dynamic mode decomposition, which had a profound impact on fluid mechanics for physical discovery, as well as in model order reduction as a primary tool based on Krugman theory. So without further ado, Peter Schmid.
Thank you. Well, let me start out by thanking the organizers and my host for this privilege of giving that lecture. It's really great being at San Diego and talking to all you people. So the talk is going to be about quantitative analysis for fluid systems, and I'm going to concentrate mostly on tools and approaches. And let me start out. It doesn't work. Okay, I think I have a little bit of problems here. Let me start out by first giving a definition. So quantitative flow analysis, what I mean by this is using mathematical or computational tools to quantify how mass, momentum, transfer, energy, and other state vector components evolve in a physical system. And it's often used to assess performance, to identify instabilities or inefficiencies or stabilities and efficiencies, or to optimize operations. Okay? So usually we have a physical system, and I'm going to concentrate mostly on high-dimensional physical systems. We have high degrees of freedom. We usually have multi-scales, multi-physics, so multiple phases, for example, complex geometry, and so on and so on. So the emphasis is really on something that is quite complicated to analyze. Okay? And then we're going to treat the system as an input-output system, where the input could be anything from initial conditions, if we do stability work, external driving, if we do receptivity work, or parameter changes, and whatever else you want to poke the system with. And then we're going to monitor what's going to come out. We can monitor lift, we can monitor drag. You know, if you have acoustic radiation, would be another objective that we're going to use. If you have a combustion system, NOx output would be another output quantity. And then we want to see how the input maps to the output through the system as a constraint, as some kind of a transfer function or filter. So what we usually do with the physical system is mostly one of three things. We're going to usually linearize about an equilibrium point. I think that's number one. Then we also reduce to essential mechanisms. So a sparsity promoting parsimony argument will be brought to bear to get really the essential mechanisms that transfer the input to the output and identify the inner workings of the system. Or the last thing that we often do is we're going to differentiate, and then we're going to go for sensitive information of the system. In that case, we want to identify how robust the system is and which parts are robust and actually observable in the system. Now, all these three categories have some standard tools that let's call. Some of them are quite complicated, but I still label them as standard tools. If you want to linearize around an equilibrium point, usually that goes with modal analysis, non-modal analysis, if you want to make it complicated, or matrix function norms, like, for example, the resolver. If you reduce to essential mechanism, we also have tools for that. POD comes to mind, DMD, Koopman, SPOD, operator inference, autoencoders nowadays with machine learning are used to just reduce it down to the essential mechanisms of the physical system. If you differentiate and go for sensitivity information, the tool of choice is adjoints. Usually they come in sooner or later, and you do adjoint looping, you deal with a Lagrange multiplier, or more recently, you have differentiable code. In that case, you do automatic differentiation to get sensitivity information. So all that on this side, I will not talk about. This is what I somehow consider the tools of the trade. I want to concentrate for this lecture a little bit on unusual, exotic things that go beyond the standard. For example, I'm going to talk about 4 different things. And that one is, what if you don't have an equilibrium point? What do you do then? Because then you cannot use anything on the standard side. So we're going to talk about multi-equilibrium systems, how to analyze them. What are the proper tools for that? Once we do the reduction, I'm going to show you 2 techniques how to get a better reduction that actually values the dynamics of the full system. And that one is residualized latent dynamics and dynamics preserving reduction. Okay, we're going to get to that one. And also on the differentiate side, when we go for sensitive information, what if you have no adjoint? Okay, what if the adjoint is difficult or maybe impossible to derive on your equation? What do you do then? Do you have other options? And we're going to talk a little bit about ensemble variational methods. Now, all these 4 topics will somehow give me the outline of the presentation. And all of them, I should warn you, are a work in progress. We have made some progress, but other ones are a little bit more a promising way forward. But it's very exciting to think about these 4 issues and push them forward. Okay, all 3 of these 4 issues, they all come with very famous names. For example, the multi-equilibrium points. We will talk about the Frobenius-Perron operator. That's the way to do that. If we do residual latent dynamics, Moritz-Zwanzig theory comes in, and dynamics preserving reduction is based on the Johnson-Lindenstrauss lemma. So they have a very good mathematical foundation that we're going to harness and get some information about our fluid system. And then we have ensemble variation. So let's start with multiple equilibrium points. Okay. So many physical systems, actually, if you look at multi-equilibrium point system, you find them more and more. Okay? For example, Rayleigh-Bénard convection has multiple equilibrium points. So that means we have convection rods that turn one way, and then just out of the blue sky, they turn around and turn the other way. Okay, and you never know when they switch. So that's what I mean by multiple equilibrium systems. Okay? The dynamo, the Earth's dynamo, is another example. So the North Pole, the magnetic North Pole pointing up is not stable. Sometimes it goes down to the South Pole, and then you never know when it switches again. Bluff body wakes is another way, is another system that has multiple equilibrium points, and turbulence as well. Okay? Turbulent bursts are a different equilibrium point from the normal background turbulence. Okay? So sometimes these multi-equilibrium points come in 2 flavors. Sometimes we have 2 or multiple competing quasi-equilibrium that are almost the same from a symmetry point of view. Okay? Rayleigh-Bénard convection is one of them, dynamos and bluff body weights. Sometimes you have an equilibrium point where one is dominating and the other one is rarely visited. In that case, we say we have a rare event system. Okay, so that causes violent, sometimes intermittent events. For example, a turbulent burst, or an acoustic burst, or a rogue wave. Okay, so here we have sorry. Wrong button. So here we have the motion, for example, for a turbulent burst, where you move on some kind of a manifold, and once in a while you have these violent intermittent bursts that bring you away from that slow manifold and then bring you back. So here is a phase space dynamics of exactly that turbulent wave. Now the linearization about the base or a mean flow becomes physically meaningless, because if you have two competing equilibrium states, the average is somewhere in the middle, but the middle is never visited, right? So it makes no sense to actually average around that middle point. You have to do something a little bit better. So this is an example. It's best to explain it on the example. This is joint work with Florence Marcotte and Yannick Ponty from the University of Nice. And we're going to go for the analysis of this type of flows that have multiple equilibrium states into phase space. Okay, that has the advantage of, once we're in phase space, we're going to have a linear operator, eventually linear operator, if we embed them in high enough dimensions. But the problem, of course, is we have high dimensions. Okay, so it's hard to analyze this one. So the way we kill this high dimension problem is we're going to look at phase space observables. For example, if we look at a turbulent flow from experiments or numerics, we don't look at all the degrees of freedom. We actually boil it down to a few observables. For example, we track the kinetic energy, the mean flow, the dissipation, the entropy, or maybe if we have a minimal channel unit, we're going to track the Fourier components of the minimal channel. Okay, so we're going to boil it down to some things that describe our physical systems. Other applications, we're going to use average quantities. I'll show you an example on the next slide, and also higher order statistics. So the example I want to use to drive home that point of what we're going to do is the Taylor-Green model, the magnetic Taylor-Green model. And that one is a substitute for the Earth magnetic field reversal. So you probably know that the Earth magnetic field here is actually, okay, died. Is actually switching around. So this is the switching process of the Earth magnetic field. And if you look where the Earth magnetic field is, okay, so as long as we have a record of the Earth magnetic field from geological rocks, and 1590 is the first one, and that one started around Victoria Island in northern Canada, and then it moved around. 1600 it was a little bit further up, and it goes further south. 1859 the magnetic North Pole was there, and since about 1970s or 1980s it's on a straight line to Siberia. Thanks a lot. Yeah. Thank you. It's on a straight line. Okay, so it's 94, 84, 94, 2000, and so on. It's a straight line to Siberia. It's actually accelerating. So something is going on, and a lot of people are now studying this. We don't have to worry too much about that. On average, the Earth magnetic field changes every 190,000 years. The last one it changed was like 500,000 years ago, so we're way overdue statistically. But a change of the magnetic field usually takes 1,000 years. Okay, so it's nothing to worry about. However, if the magnetic field of the Earth is changing, we're gonna not be sheltered or shielded by the magnetic wind that comes. So it's gonna be pretty much a disaster. Okay, while we're doing it. Here's another picture. So you see that from 1904, we're on a straight line, and we're gonna shoot over to Siberia. Okay, so how do we model that? How do we model that? We could come back from Siberia, of course, right? So it doesn't mean it's going to go south, but it could be. It could be. So the magnetic Taylor-Green model is basically an MHD problem. Here the governing equations. We're going to solve that one in a triple periodic box, 64 by 64 by 64. with Fourier modes. Okay, we have a zonal forcing. And if you look at this one, if you look at the magnetic field, the reaction coordinates that we actually observe is the velocity in x and y and the magnetic field in x and y. So we are four-dimensional, okay? And it's averaged over the bottom 1/8 of that cube, okay? And if you plot that one just for Bx and By, you see that Bx, the magnetic field, goes up and down and up and down. If you actually discretize this one, then you actually see that we have four different states from four different quadrants. And here is quadrant number 4, number 3, then it goes back to 4, to 3, and so on, then it switches to 1, and so on, and so on. So you see this intermittent switching with multiple states. We have four different states. Okay, so if you put that one into phase space now, and I'm going to ignore the velocities for now, I'm going to go two-dimensional in Bx and By only, you actually see that this kind of spaghetti is the phase curve in a two-dimensional phase space. Okay, so ignore this one in the middle. This is just a transient how we started out. We should have ignored that one. But once it's in quasi-equilibrium states, it more or less changes between these four different equilibrium states. Okay, so just by looking and plotting this one, we can identify that there are four metastable states with a long residence time. So once we're here in this corner, we actually go around and stay quite a long time in this corner. But then there's also transitory routes between these four corners. And that one is signifying a rapid transition between these four equilibrium points. So we have intermittent switching from that picture for right now. We can only deduce that we never go through the middle from this one here diagonally across. We always go in a circle, but either counterclockwise or clockwise. We never know where we are in these four corners. Okay. So how do we analyze this one and get some physical understanding and mathematical underpinning so that we can do our analysis? Okay, so we're going to be in four-dimensional space. I'm going to plot it in two-dimension, okay? And we're going to discretize the phase space in uniform hypercubes. There are four-dimensional cubes. I'm going to show you only two dimensions here. And we're going to track our phase curve as I plotted on the previous slide. And we're going to basically assign every little point on this curve here to this box. And then once we get outside of this box, we're going to start a new box and so on. We're going to trace out that curve. Okay? We're going to make a list of all the boxes that we gather up by following that trajectory. If we come back to a box we already have, we just add that trajectory to this box. Okay? And then we keep on going. So by the time we trace out the entire phase curve, we more or less have a discretization in terms of cubes in phase space of that trajectory. All right. So then, what do we do with this one? We're gonna treat each cell here that we have as and assign a probability to this cell or a density to this cell. Okay. Then we're gonna postulate a conservation law that models the flux of this density from cell to cell with a specific flux function. And that flux function, of course, has something to do with the dynamics of our system, right? That's the one that moves us from one cell to the next cell, okay? So this is based on the Liouville equation. This is a Liouville equation that determines the flux of densities or probabilities across the box boundaries. And based on that flux of probabilities, where we go next from one box to the next, we can actually introduce an operator that is known as the Frobenius-Perron operator that propagates the density in one box integrated over a box and relates it to the density that we had one time step back. This S-1 is basically one time step back. Okay. So here's a picture. This is the density that we're interested in, and we want to know where does that come from. And the P, that operator here, is basically mapping where we come from to where we're going. Okay, so that brings the dynamics of the phase space back into the equations. So how do we do that practically? We're going to compute the probability of finding a snapshot of our phase space curve in box BI that has been in box BJ one time step earlier. Okay, so this one results in a Markov process or a Markov transition probability matrix. So this equation here, if we discretize that one and use it in terms of box counting, is written here. So this is the number. This is the number of trajectories in box BI that were one time step back in box BJ. Okay, divided by how many snapshots we have in BI. That gives us a probability. Okay, so for example, in that picture I had before, this red little area, once you integrate that out, tells us the probability of going from this box back into BI. This here is a measure of probability of the trajectory coming from here and ending up in BI, and this one here to BI. This orange one up here is the trajectory that stays inside the same box over one time step. Okay, so by doing this one, we're getting a matrix of transitions between boxes that encodes the entire dynamics of that snapshot sequence. Okay, so once you have that one, the box size, by the way, is very important. If you make the box size too small, then you have a very good resolution of the dynamics. You follow it very, very finely, okay? But not very many snapshots end up in a small box. So they get the bad statistics. Okay? If you make the box size large, you have a good statistics, but you have a very coarse discretization of your phase trajectory. Okay? So for the experimentalists, usually I have experimentalists in the audience, I don't know about here, they immediately recognize that this is basically a particle image velocity where you take two snapshots and you correlate them to get the velocity out. Okay? So this is PIV in phase space, so to speak. Okay. All right, so once we have this one, what do we do? Now, what can we learn from that matrix P once we form it like this? Okay. We recognize that this is rho stochastic. So that means the probabilities of coming from somewhere and ending up in one box has to add up to 1. We have to come from somewhere, right? So that means that we have a unit eigenvalue of that matrix here that gives us the stationary distribution. That's like the mean flow, the mean distribution over the entire phase space. Okay. Any eigenvalue close to 1 is the distribution of phase space configurations over persistent states. So an eigenvalue of 1 doesn't move at all. An eigenvalue close to 1, but less than 1, moves very slowly. Okay, so these are motions that stay the same way. They're very, very slow dynamics. And small eigenvalues are the transitory states. They move very fast. Okay, so by just looking at P, we can already sort out the fast modes from the slow modes. Okay? And then the associated eigenvector that goes with that are the regions in phase space. So once you have that, when you can further break that one down, you have your matrix P, and now we interpret P as a graph. Okay, so each box here is a node on the graph, and then you have a probability of staying inside the same box. So this is a 61% probability that you stay inside that box once you start in that box. And then you can connect these lines of going to neighboring boxes. Okay, so this is like a flow on the graph. And once you have a flow on the graph, you can actually start to work with that one. We're going to cluster this one into communities. This is done with the Louvain algorithm. So we're going to gather up similar boxes into bigger clumps of boxes. Okay. We also lump the communities further on with a minimum spanning tree. I show you how to do that one. And then we're going to compute the transition probabilities to go from one section on the graph to another section in the graph. Okay, so all this dynamics is now turning into a graph problem. All right, so here is the clumping. We take our matrix here, or our graph here. Okay, that's the P matrix we start out. And we hit it from both sides with a clumping matrix that looks like this. So here's the box ID that we have, and here's the community ID. Okay, so that means all these boxes here are in this community here. Okay, so if you hit it from both sides, you basically homogenize the entire graph into bigger clumps that belong together. Okay, and if you do that one, you basically multiply it on both sides many, many times. Okay, then you're going to get a better approximation, or in terms of coherent structures, a more systematic approximation of that dynamics. Okay, so here is a P matrix as we start out. We have about 500 of these boxes that we started out with. That's the initial discretization. And we can already see that this one has something on the diagonal. So on the diagonal is always the resting probability of staying inside the same box. Okay. Then we have some kind of a gap here where it's pretty sparse. So this would be a group of boxes where we go through really, really fast. Okay. And then we have another one that has a high resting probability. So if you do that 5 times, for example, you clump, you recompute, you clump, you recompute, and so on 5 times, you're going to get at the end, instead of 500 boxes, you only get 35 or 33 communities that are made up of big clumps of boxes. Okay? And then you see this one is totally empty. So this would be a community. All the boxes that belong in that red square are boxes, or is a community where we go in, next time step we go out. Okay? We're not resting anywhere because it has a 0 resting probability on the diagonal. Whereas this one is a community that has a high resting probability, and this one so-so. Okay, so by doing this one, we can actually get a really nice hierarchy of persistent states that stay there for a while, and other ones that are just passed through. These are fluctuating or very transitory states. Okay, so this is the way we analyze this one. Okay, so for our model here, these are the families that we organize, the communities that we organize in terms of phase space that actually belong together. Okay, so but this can only get us that far. If we want to have more, the first algorithm is basically fizzling out. We cannot do anything more. We have to do something else. And that's when we throw in something called minimum spanning tree. And the minimum spanning tree is basically, once you have the communities, you calculate one graph, one connection that connects all the boxes, but with the minimum cost. And remember, the minimum cost is the lowest probability. And then we find the connection with the lowest probability. That means that one is never used very often. It's very, very unlikely that we're going to go between these 2 boxes if it has a very, very small number. And that's when we can cut it, for example, and say, okay, this is a community, this is a community, and that thing we cut was not used very much anyways. Okay, so we can further and further cut that down until we have enough structure to analyze it. Okay, and then this is basically, if you do that minimum cutting again, you see that it gathers more and more and more. Okay, we more and more identify these big states here, transitory states here and here and here and here. Okay, so if you do that over and over again, you can actually get the entire dynamics that is encoded in phase space out there quite nicely. Another thing that we can do is, let's say we're here, okay, and we actually want to end up here in the fastest possible way. So this is an optimal transport problem now, where we have we look for the minimum or the most likely path that we take from here to there. And this is like a navigation problem you have in your car. If you want to go from A to B, you're going to solve a Dijkstra algorithm, it's called, which gets us in the graph the cheapest path and the fastest path from going here to there. And our way of doing cheapest is the highest probability of actually going from A to B, because that's the one that we most likely will see. Okay. All right. So this is what we did for the magnetic field. We also tried that out, and this is a joint work with Ru Yang from Princeton with the convection. Okay, so here is the convection and we have an intermittent reversal of the roll direction. So you have a box like this, and it can either roll counterclockwise or clockwise, and it changes anyway, anytime it feels like it, so to speak. Okay, so here is the fluctuation. These are the first two POD modes. It can be described by just two POD modes. That's quite nice. So it makes it low dimensional, nice to play with. And you see that it rolls, counterclockwise, clockwise, counterclockwise, clockwise, and you never know when the next switch comes. Okay, and we do exactly the same thing. This is the phase space. Now it's in two-dimensional. This is POD1. This is POD1 2 coefficient. And we're going to do that. And you can already see, oh, it clusters here, it clusters there, and it has a transition from here to there, and a back transition from here to there. Okay. And then you discretize that. These are our boxes again. One more time, the boxes. We're going to count how many fall in the boxes. All the ones that are never visited, we don't even store those. Okay. And then we do a graph. So this is the graph of self-interaction or next interaction. And he even did it, high resting probability is a big circle, low resting probability is a small distance. Okay. And if you do this one, you can actually then cluster it. Okay. And in our case, we don't have to do minimum spanning tree. The Louvain algorithm gives us nice 6 clusters. Okay. And these are the clusters, and these are the structures that are represented by the centroid of these clusters. Okay. So over here, this is the this is the clockwise. This is a transitory state. This is when this one switches to the other side and goes counterclockwise. We're going to go through this one. So this is the centroid here, and this is the centroid there. So you can do this really nice analysis for fluid systems that have multiple states. Okay. Now, if you change the Rayleigh number and the Prandtl number, for some Rayleigh and Prandtl number, you don't get that switching. Okay. And you can still do the same analysis, little pointless here, but you're going to get just 4 equally likely clusters. Okay. This is the one we analyzed. Rayleigh number is 2 times 10 to the 8. Prandtl number is 4.3. You get the clusters that we analyzed. If you go lower in the Rayleigh number and lower in the Prandtl number, it's a little bit muddled up, but you can still do the same analysis. Okay. And if you do a higher Prandtl number here, again, it's just a mess. Okay. But you can still do this type of analysis. Okay. So this is the problem number 1, multiple states. What we have to do is we have to go into phase space, discretize phase space, and then look into probabilities of transitioning from one box to the next. You have a question?
Oh, just kind of maybe very superficial, but this M-like shaped curve looks very kind of similar to the mapping or usually people drawing for the strange attractors. Any relations, or this is just?
Well, this is a little bit, this is more like the manifold that we actually.
I understand, but
flow
the same story kind of goes with strange attractors.
Yeah, I mean, this has very close connection, or it looks the same as the Lorentz attractor, where you have one side of the lobe and the other side of the lobe, and then the Lorentz attractor has a saddle point at the middle. This one has actually 2 different paths for forward and backward.
But there are many strange attractors.
Exactly. Yeah, that's a very good point. Yeah, thank you. All right. So let's get to the second one. The other ones go a little bit faster. Okay, and that one is residualized latent dynamics. This one is a topic in model reduction. Okay, we have a high dimensional system. We want to make it smaller, but by making it smaller, we have to be very, very careful that we don't throw out the baby with the bathwater. Okay, so smaller is not always good if you don't do it right. So this is a closure problem, and the key issue of any model reduction application is a closure problem. How do you actually account for the things you throw out? Okay, so the influence of the retained scales of freedom on the dismissed structures is very, very important. And for a proper closure, you have to model somehow the effect that the effect of the degrees of freedom that you throw out on the ones that you keep. Okay, you cannot just cut and throw it out and hope that everything goes fine. You have to somehow account for the cumulative effect of all the things you threw out on the ones that you keep. Okay, so this is what we usually do. We have some identified structures, okay, lined up as columns, okay, PUV modes, for example. And then you decide on some kind of a cut point. These are the guys you keep, and these are all the guys you toss. Okay? So the truncation point is often selected by energy arguments, singular values, for example, when you actually should do the sensitivity. For example, if you have aeroacoustic modes, if there's an acoustic mode here, it could have a small energy, small singular value, but still be very important. So this is a topic for another talk. Okay. And the feedback loops can play a very, very significant role. Okay. So now if you write down the equation for the retained modes, okay, only the retained modes that we keep, you can write this down as RT of the full modes. Okay, this is a full mode. We only keep a few of them. And then if you do this one and bring it back to a consistent ODE in that case, of only the retained modes, this is the operator you get. Okay, and this operator immediately partitions our system matrix into retained onto retained, retained onto dismissed, dismissed onto retained, and the way the dismissed interact with the dismissed. Okay, so you partition that out really nicely. Now, eventually, what we want is we want to have a dynamical systems only on the retained modes that is self-consistent. Okay, so the way to do that is we have to somehow wrap all these pieces of the matrix, fold it into the retained modes. Okay, there's a technique for that one, and that one is known as the Schur complement. So I have an ODE here. That is, the retained modes are governed by ARR. That's the dynamics of the retained modes among themselves. Okay, but they're driven by the dismissed ones. That's the ones we throw out. And then we have the equation for the dismissed ones. They depend on the retained ones and the dismissed ones itself. And I want to solve the second equation for D and plug it into the D up here to make the R self-contained. Okay, and the way to do that, if you do that properly, this is what comes out. This is the ODE. The evolution equation for R, of course, depends on how R interacts with itself. And then this long expression that only has an R in it. Okay? So all the pieces of our matrix have come in. Okay? But now the bad part is this is an integral differential equation. Suddenly our equation is more complicated than it was before. Okay, so this part here, if we truncate this and ignore this, this is a truncated system. Most likely that will blow up on you. Okay. This part here is the residualized system. So we take the residual and fold it back into the retained modes. And this piece here in the integral is the influence of all the dismissed scales on the retained scales. Okay, that's the closure problem. Now look at how that is. We have the retained modes, that's just a few. We go through this matrix here that goes from retained to dismissed. So we're going to go high. This piece in here is the expensive part. This is high dimensional to high dimensional. This is huge. Nobody does that. I can just write it down mathematically. And then once we have that one, we go back to the reduced ones. So this is low, high, back to low. The whole equation. Exactly. Good. So let me skip over this one. So what we actually do, the idea, the full idea here is in the linear case, the kernel, this piece inside the integral can actually be identified. But for the nonlinear case, the kernel can be modeled by an autoencoder. So this little integral piece that is so important to close it properly, we actually going to learn from the data. Okay, we're going to throw in an autoencoder that learns that one and closes it out properly. Okay? So in the end, the kernel by itself goes from low to low, right? That's the nice part. So if you ignore that it has to go through high first and then back to low, we're going to ignore that one and go directly from low to low. Okay, so it should be actually quite nice to learn from an autoencoder. But what we actually have to do is we have to imitate the linear design that is low, high, low. Okay, So let me show you that on an example, and then it probably sinks in a little bit better. This is work with George Rigas from Imperial, and that one is the closure of a harmonically balanced Navier-Stokes equation. Okay, here is the equation. This is the PDT term, but this one is now Fourier transformed, so it's I omega. Okay, this is the linear part, and this is the nonlinear part. Okay, and it's in frequency space. So that means if we keep all the nonlinearities, all the frequencies talk to each other through triads. That's from the U grad U. Okay, all this is the nonlinearity part. Okay, so this is an example where we keep 4 frequencies. Okay, and here are the 4 frequencies. This is equation number 1. This is the 0 frequency, and that one has a nonlinear interaction between all the higher frequencies and their negative equivalents. Okay, all of them feeding into 0. That's equation number 1. Equation number 2, you get the idea. This one looks at the frequency 1. That one is all the interaction that go into frequency 1, and then 3, and then 4, and the next one. Okay, so this is the entire set of equations, and then we make the decision. We want to have a closed system, properly closed system that only tracks the 0 and the first frequencies. And these are the dismissed frequencies that we need to fold into the first one. Now, this is not linear anymore. We cannot write down that integral. Okay. So for this one, we're going to formulate it like this. Okay. This is low to low, low to high, high to low, and high to high. This is the ones we keep. This is the ones we dismiss. Okay. We want to eventually have an algebraic equation for low to low only, self-contained. Okay. So this one needs to be closed by a residual. And we know how that residual looks like. Okay. If it's written down like this as a matrix, this one is low to high, the high to high, that's the big one, and then back from high to low. Okay. So if we learn this entire package here from low to low through high, we're going to model by an autoencoder. Okay. But now the autoencoder has to be designed in a very, very specific way. Okay? And the autoencoder has to inherit the relative dimensions of the linear Moritz-Zwanzig structure. And the linear Moritz-Zwanzig structure was low to high and high to low, right? We cannot ignore that one. It needs a high-dimensional reservoir in the middle so that it has enough degrees of freedom to express the low to low properly, okay? And the way to do that is an autoencoder, right? So this is an autoencoder that is actually fatter in the middle than it is at the end. So it's an inverse autoencoder. Usually autoencoders go down in dimension. This is one that actually has a little reservoir in the lowest point, in the middle point. Okay? And this one doesn't have to be all that high. Okay? This one is, if this one is just double the ones you have on the sides from low to low, this one is enough. So you don't have to go all the way and make it expensive. And you see that if you run this one, the residual, this one is the full simulation. Okay, this is the ground truth that comes out. And if you do this one and learn this one, you get pretty much the same as you have over here. We also tried this one where we reduced the middle layer and didn't give it that high dimensional reservoir. It didn't work. It just blew up on us. Okay, so this one is where we learn from the linear part how to design a nonlinear autoencoder. All right, next, we're going to do a dynamics preserving reduction. That again is a reduction down to from high dimensional to down to low dimensional. Okay, but now we don't want to residualize it. I'm going to show you another trick, and that one is we want to actually preserve the dynamics of the full state as we reduce it down to the lowest state. Okay, is there such a thing? So, is there another method for encoding the temporal dynamics in latent space? Usually, when we just take an autoencoder that goes down to latent space, the dynamics of the full state is not the same thing as the dynamics in latent space. Okay, so this one mixes up everything. Okay? And we want to actually preserve the temporal dynamics. Okay? So one way of doing it, I just showed you, is introducing a memory term. That's one possibility of getting a proper closure. Okay? Then we don't care how much we mess up the low dimensional dynamics because we know how to close it out. The other one is called delay embedding, time delay embedding. That one goes back to Ruel and Calkins. Okay? And the ones that I want to introduce is called locality sensitive hashing. And that one is on the Johnson-Lindenstrauss lemma. Okay, so let me explain. The idea is we linearly reduce the incoming dimensionality, but we preserve the temporal dynamics as we do it. Okay? So if you do POD, DMD, SPOD, ICA, whatever your favorite linear reduction is, they all influence space and time together. You reduce the space, I agree with that, but you mess up the time. You mix the frequencies, you do all kind of things. Okay. So the question is there a dimensionality reducing embedding, projection down, that preserves the temporal dynamics? And the answer is yes, there is. And there is a really beautiful theorem or a lemma, the Johnson-Lindenstrauss lemma, that guarantees that there exists an embedding of this type that does it. Okay. So here is the one-line Johnson-Lindenstrauss lemma. And what does that say? If you have a snapshot basis here, these are the snapshots, okay? And here is space, is this, and this is the time direction is here. So this is snapshot 1, snapshot 2, snapshot 3, 4, 5, all the delta t apart, okay? And now I'm gonna apply a mapping here, okay, that brings that dimensionality down to this size, okay? And then we have the reduced space. And now this is still time, but space has been reduced. Okay. Then if I take any member out of here, pick anything you want to, the 7th snapshot. And I pick a second one, the 35th snapshot. And I take the difference between them, how far they are apart in time. Okay. And then I take the same thing, the 7th here after it's reduced, and the 35th here as it is reduced. Okay. And I take the difference of these two guys, it's the same. It's really astonishing, right? And it's not quite the same. There's a small distortion to the low side. So maybe it's 99% the same. Or to the high side, it's 101%. Okay, there's a small distortion that I can set. The epsilon I can choose. Okay. So this is the embedding, this is a distortion factor. And the bad thing about this one is, okay, this one is the bounds, these two bounds that guarantee that the distance between any 2 points in my snapshot basis are preserved in distance is not always true. It's only better than 2/3 of the time we have it. Okay, so there's a small failure probability. I'll talk about that in a second more. Okay, so the question is, why does this theorem here, why does that preserve the temporal dynamics? Well, look at it in phase space. If these are the snapshots, okay, and this is your curve in phase space, and you know that any pairwise distance between any of these red dots is not distorted. This is like a straitjacket on the phase space, right? It cannot do anything else. That means the distance between the projected ones and the original ones cannot do anything else than preserve the dynamics within the distortion factor of epsilon. So mutually pairwise distortion bounds preserve the dynamics. But now the million-dollar question, of course, is what is that magic phi that does that? Okay. And how can we construct the embedding? And that one is known as the fast Johnson-Lindenstrauss transform, or for short FJLT. Okay. Obviously, phi is a matrix that takes the original number of degrees of freedom and gives it the reduced number. Okay. So it's a rectangular matrix like this, just like I drew it before. And that one is done in 3 steps, P, H, and D. I don't think it has anything to do with PhD, but that's how they did it in the original paper. Maybe it's a joke. So let's talk about the H first. Okay, this is some kind of a spectral decomposition. Okay, so we do think of it as a Fourier transform. Here we do a very special Fourier transform with wavelets. You can pick anything you want. The Fourier transform works just as fine. Okay, so this one turns any vector, any state vector into its Fourier transform. Okay, so it sorts it out in terms of structures, hierarchy. Then we're going to take this one. This is the one that does actually the reduction. This one is a stochastic matrix that does the randomization. So what this one does is, once we have the Fourier transform, it picks very few points on that Fourier transforms, not all of them, very few, sparsity of about 1% or less than 1%, and picks it out. Okay, and that's enough to preserve the temporal dynamics. Now there's one big problem, and that brings in the D matrix. What if I give you a sine curve? A sine curve here. Then I Fourier transform it, and it only has one peak. Okay, and the rest is 0. If this one grabs something and misses the peak, you have a vector of 0, right? That's not good. Okay, so in that case, we want to have a broad spectral support without messing up the system, without messing up the vector, sorry. Okay. So in that case, we're going to do a D first, and that one is a diagonal matrix that has pluses or minus, +1 or -1 on the diagonal, randomly shuffled together. Sometimes a plus, sometimes a minus, okay? Half-half. So what this one does is, it of course messes up the Fourier transform, but the spectrum is almost recognizable from what it was before. Okay, so we're going to multiply our signal and flip signs randomly. Then we send it through a Fourier transform, and then we pick a few of the wave numbers that we have. That's the technique. It's simple as that. This is order n. This is n log n. This is n. It's even fast. Okay. And once you do this one, how far can we actually reduce? Okay. We can reduce logarithmically in n. That's a really, really strong reduction. Okay. Of course, the epsilon comes in. The more we don't allow it to distort, the less we can reduce. Okay. But if we say 5% is good enough, we can distort by 5% plus or minus, then we can reduce by quite a bit. Okay. And this is the sparsity constraints. And there was this other thing that I mentioned, and that one is it's only good 2/3 of the time. Okay, that's not so good because 1/3 of the time we mess up, we go over the bounds. Okay, but the fail probability can be improved by doing a higher linkage. We always have pairwise connections. That's what the Johnson-Lindenstrauss theorem says, pairwise connection. But there is a version where you say, okay, don't compare pairwise. How about 4 snapshots that I take randomly out, and they all have to satisfy the same thing. And then the failure probability goes way, way, way down to a point where we don't even bother. Okay? So that one can be done. Okay? Instead of pairwise distances, we consider distances within bigger groups. Okay? So 2 is just a small group. So as we do this one, as we link more and more, we should actually compare the higher linkage should be compared to time delay embedding for a fair comparison. So even then, the compression rates are even higher. Okay, so let me show you this one. So this is convection in a sphere, spherical shell. This is more or less what it does. Okay? It's something that has to do with the sun, the convection on the sun. Okay, Rayleigh number is 4 million. That's above criticality, so that thing goes and goes and goes. Okay, this is a surface mesh with a radial finite difference. Okay, degrees of freedom 2.7 million degrees of freedom we have, and we're gonna choose a maximum distortion of epsilon is 1%. Okay, this is our, so we go maximally 99% or 101% in terms of distortion. Okay. And if we do an SVD on that one, this one is the second POD mode. The first one is a little bit more boring. This one looks better. This is the second POD mode. And if we do that one on the full data set, unreduced, it takes 157 seconds to get that mode. This one is where we first reduce the data matrix, and then we do an SVD on that one. Okay? And this is the space part, and this is the time part. And this time part over here is almost the same, within 1% of the one over there. Okay, and if you go and recover the PUD mode here, it takes 4 seconds to get this out because it's so much more reduced. Okay, so this is quite impressive. So some extensions, the FGLT is a linear autoencoder, obviously, right? This is based on 3 matrices, so it has to be linear. But then once you have the latent space, the nonlinearity rests in the latent space. So we have to actually have a nonlinear latent space model, for example, spectral submanifolds, SSMs. That's coming up now. And also the other extension that we're looking into at the moment, the Johnson-Lindenstrauss lemma actually compared the distances between 2 vectors in our snapshot basis. Okay. Now, the distortion in norm can be related to the angle between the points. So if you actually preserve the distance between any pair, you also preserve the angles between them just as much. Okay? And once you have the angle preserved as you reduce it down, the subspaces that they span are the same within a small distortion. So anything that we do with Krylov subspace techniques can actually be FGLT before and then sped up much, much, much more. Okay? So that's what we're currently looking. This one is basically then the Krylov subspace techniques on steroids. All right, and then really quickly, the last one, and that one addresses the fact, what happens if you want to have sensitivities or you want to optimize your fluid systems, but you don't have an adjoint, or the adjoint is so complicated to do, you have multi-phase problems, you have bubbles and drops and shocks and who knows what else, and it would be a nightmare to derive the adjoint. Is there any alternative? Okay. So sometimes it's very tedious and error-prone process, particularly for nonlinear and multi-physics system. So an alternative is the introduction of a response or a surrogate surface formed by evolving an ensemble of particles in the flow. So differentiating this surrogate surface instead of the equations is the way to get the sensitivities. Okay. So let's say I have a control variable U, I have a state variable Q, and an observable Y. So this one is the state equation. So we have a control variable, we stick it into our Navier-Stokes solver, and then we're going to get the state. Okay. So this is maybe an integration over a long time or something like that. Once we have the state, we evaluate certain things about that state, for example, the drag. And that one is our output. Okay, so going directly from U, the control, to the output Y. Okay, so the optimization that we're going to do, we introduce a cost functional. This is the output Y that we have. Okay, and we want to have it as close as possible to something that we measure. If we don't measure anything, M could also be 0. Okay, so M is a target observable. If you don't have a target observable, it could be the skin friction or something like that, then just M is equal to 0. R is a weight just to play around a little bit. Okay, so we're going to introduce N control variables. Okay, so we're going to try N different controls. Okay, we gather them up, and we also have the mean. So the mean of all the controls. Just average it out. Okay, and then we express the U, the control, as the mean plus a weight on exactly these differences. So this is like making a surrogate surface out of finite differences in its neighbors, in its nearest neighbors. Okay, so if you do the same thing with the observables, okay, so this is the observable side, then your cost functional suddenly is the mean observable, the observables expressed in that same weights that we had before, minus the target. So now you have this expression here just from a surrogate surface that you actually fit through the many controls. And then with this one, we just have to get dj, dw, here the gradient. You can differentiate that one in one shot. You can also get the Hessian if you need that one for some reasons. This one is an even simpler expression. And then once you have that one, you can solve for the weights, the magic weights that puts it together. And that one is your next control, right? So you actually iterate, you do a gradient descent on the control without ever having an adjoint. The adjoint is that surrogate surface that we patch together by having a bunch of particles, trying out a bunch of controls, and then putting a surface through it, and you differentiate the surface instead of the equation. So this is a very good way to do that one. And with this scheme, we can accommodate any governing equation, whether you have a Rand's model that is very simple, or LES, or DNS, or PSE, any equation actually can be that any. And then we treat even turbulent flows that usually diverge when you have adjoints. Okay? And we also don't need to store fields for nonlinear adjoint looping. So final thing, this is where we tried it out. We do a shape optimization of a wall to minimize drop pinch off. So we have a drop hanging there on the ceiling, okay, on a wavy wall. And then eventually that drop, comes down, and a little bit of a drop stays behind, and most of the drop ends up on the bottom. Okay. And now we want to change the shape of that wall such that the volume that ends up at the bottom is as small as possible, and most of it still hangs on the ceiling. Okay, that's just sort of a play problem. Okay, and if you do that one, this is the way we optimize that one. So in the beginning, 92% and 92% or something like that of the drop falls down. And if you keep on optimizing that wall, which has, I didn't even write that down, has 8 Fourier coefficients to play with. Okay, that's the control. Okay. At some point, after we fizzle out and plateau out, we're going to have a drop that is 60% only on the bottom, and the other 40% still hangs at the ceiling. Okay, so doing this one with adjoints would be a nightmare. But with this one, and just having about 8 of those particles to put a surrogate surface through it, we actually do quite fine. All right, so this is the summary then. We talked about 4 different problems. We had multiple equilibrium points. The way to do that one is going into phase space and doing your transition probabilities between the cubes, and then use graph theory to partition out what belongs together and what is persistent and what is really quick acting. Okay, so this is the way to analyze these type of systems. Once you do a reduction, be aware that your encoder that you have here is producing a latent space that needs to be closed properly. And closing it properly means that you have a low retained mode, but then you need a bigger reservoir from low to high and high to low back down. So the inner part has to look like this one, and then it will work. Okay, the rest can be learned. If you do dynamics preserving reduction, you get a huge reduction in space by still preserving time. So anything you want to know about time, you can still do in latent space because it's preserved. And if you need a derivative-free optimization, use a bunch of particles, propagate them along, differentiate the surrogate surface that you put through the particles, and then you can do optimization without doing the adjoints. So with this, thanks a lot for your attention. Sorry, I went a little bit over. Thank you.
We're a little bit over time, but maybe we have time for a question.
Yeah.
Very nice. So I had a question about the residualized latent dynamics. So let's say that I had a flow, and the metric of the flow depends on the Reynolds number. Then does that reservoir have to increase with Reynolds number, or is it invariant with Reynolds number?
By experience, it doesn't have to scale with Reynolds number. So it depends a little bit how radical you want to reduce it. Right? So if you reduce it by quite a bit, and there is a lot of dismissed scales, your reservoir has to be a little bit bigger than the parts that you retain. Let's say you retain 5 modes, and then in our case we retained 2 modes out of a total of 5. Okay, so 2 modes. If we make the inner one 3 or 4, that's already enough to capture everything. Okay. If you reduce a high resonance number flow down to, for example, 5 modes, you're not going to get away with just 10. You probably will have something like 50 or 70, or I'm just guessing.
Depends on the
Yeah, it depends. It depends a little bit on how much you throw away compared to how much you keep.
And maybe it also depends on the type of flow, right? Because
Yeah.
if it's like a boundary layer,
Yeah.
then that's probably more sensitive to resonance number.
I would think so. Yeah.
Than these convective rolls or rates
Yeah,
and
yeah.
so on, right?
It depends also, it depends a little bit on the memory length, right? Because in that reservoir, you encode the memory length.
Yeah.
And that one is the eddy turnover time usually.
Yes.
After one eddy turnover time, it's a fresh flow. It doesn't remember where it came from. And depending on what the eddy turnover time is, you may have to make the reservoir a little bit larger to accommodate this much memory. Yes.
I don't know, do you know or not, but there is an exact solution of the water evolution of water on the ceiling. So you may be interested.
Yeah, I'm very
Hear
interested
your
in that.
results with
Yes.
that exact solution.
Yes, absolutely. Yes, thank you. Very good. Would be nice to compare. Yes.
Professor Schmid, so for me, I'm interested as a student to basically learn about fluid dynamics and heat transfer to eventually work with the U.S. Navy for designing submersibles or vehicles. What kind of things in your experience on line of work with fluids and a lot of this, which I'm not familiar with yet, should I really be taking a look into?
Oh, yeah. What kind of fields you should study? Is that, or what kind of
I think that's part of it. So I'm from structural engineering, so it's completely different.
structural engineering? Yeah.
But I'm really interested in integrating what's called a lot of the mechanics in the M&E department into my own self-study because I want to work for the U.S. Navy. And all of pretty much being in the fleet means that you want to be able to have a huge understanding of fluids and also heat because the oceans are pretty much very interesting.
Yeah,
to say
yeah.
the least.
I mean, what I showed you is way beyond a curriculum. So this is an unrelated question, but I don't know. I would go through the usual fluid dynamics curriculum from the fluids 101 all the way to more specialized fluids, with a heavy emphasis on probably mathematical theories for PDEs and for numerical simulation of these PDEs. I mean, that gives you a really good foundation to work on. Sorry, I cannot be more specific.
Thank you.
Okay.
Okay, well, that's,
Yeah, there's one in the back.
All right, so in the
One minute.
last part, you talked about the randomization, where the computational complexity increases exponentially with the dimension of your, let's say, the variable. So, but in the second and the third part, you talk about the model reduction. So I was wondering, how does that model reduction part contributes to, help you like simplify or say become more efficient in your optimization part?
Well, if you reduce it down, you basically force the system to only retain the essential mechanisms of the flow, right? So you have a high degree of freedom system, but its information sparse. So that means in a properly chosen basis, it can be expressed by a lot less coefficients than you have degrees of freedom in the beginning. So by doing that model reduction, you actually force the system into just bringing it down to the essence of the mechanisms that drive it, right? So you want to retain the overall dynamics and the spatial resolution that you have, but you want to do it with the minimal number of structures. And that's basically taking everything out that is not important and keeping everything that is important. This is the way the analyze flows. We cut the fat and we look at the meat.
You have time?
No.
yeah, ask your question real quick and then we're gonna call it a day.
So you decided to use the Markov for finding out the structures.
Yeah.
Have you thought about like defining a punishment for the agent and actually like controlling stuff with that?
Yes, sorry, that was on the number two
That's
with the
multiple
a
equivalent.
multi-equivalent with a Markov.
Yeah,
What
yeah,
is
so
that
it's
question
like
again?
reinforcement learning, for example, for like a chess. Have you tried to do that like to control maybe something much simpler than that?
No, we haven't. The parts about the control that we talked about, and that one I talked to Miroslav, is basically when you're in a part of the phase space where you have a very persistent dynamics, okay, and you want to prevent the flow from switching to the other one. When you're in the persistent dynamics, there is no point in controlling it because you're not even close to switching. Right? So you could use event triggered control. So that says when you get into a box that has a high probability of going over to the other side, that's when you switch on the control and say, okay, I need to bend it back and keep on the side that I want.
So we can still prevent getting to Siberia? We can still prevent the North Pole from.
How do you do that? I don't know. I think it's already on the way. Who knows?
You know, once it goes to Siberia, it's never coming.
It's never gonna. It's gonna get. Yeah.
It's gone.
Or can get the law for that.
Yeah.
Okay, let's thank Peter
Thank you.
again.